afternoon, everybody. And first of all, thank you to Triskem for the opportunity to bring you up to speed with some of the new innovations that we've been working on at RADEC. Obviously, with the current COVID situation, we've had maybe a little bit more time to think about other innovations, and we've got a few developments which hopefully would be of interest to some of you. So basically, I wanted to introduce some of the changes that we've been making to the standard pyrolyser system, some changes that we've been making to the Pyrolyser mini system, and then also some developments on hardware and consumables. So I'm going to start off with talking a little bit about the Pyrolyser Gen III, Generation 3. Now this system is very similar to the current systems which are on the market and which many of you probably use. But we've identified a few changes to the system which we think are going to help maintenance and repair. So basically, for many of the systems that are installed in laboratories, the furnace itself is located within some sort of enclosure, some sort of extraction hood, and it's not necessarily that straightforward to access the side panels or the rear panel of the furnace, which means that when any sort of servicing is required or any repair work is required, that the furnace has to be moved from its enclosure. So what we have done is to redesign the furnace, and in particular the electronics compartment of the furnace. And we've now moved all of the main controls to the front panel. So whereas before you'd have had over temperature controllers, you'd have had your emergency stop switch, and you'd have had your connectivity located on the side panels, these are now all located on the front panel. So that makes it slightly easier in terms of use and in terms of seeing particularly the over temperature controllers. But this has also enabled us to make a bit more of a substantial design change to the furnace. So what we now have is the furnace electronics compartment is on a tray, and that tray can be pulled out from the front of the furnace. And that gives us access to all of the electronics components and all the pneumatic fittings within the furnace itself. So in effect, that will allow us to achieve most repairs, most servicing activities without physically having to remove the furnace from the enclosure. We can literally just remove some of the securing screws, pull the tray forwards, and then access the electronics compartment from the front of the furnace. So that's quite a significant change in terms of the furnace design, and as I say, it does facilitate maintenance operations. Stage on from this looks very similar apart from the controllers, and this next generation of furnaces which we are currently working on is not actually available at present, but we're hoping to make available early next year, hopefully the first quarter of next year. Use the same layout as the Pyrolyser III furnaces, but instead of the standard controllers, the Eurotherm 3504 nanodac controllers, which are currently on the Pyrolyser systems, we're switching over to a much more user-friendly HMI interface. So this is a sort of a touch screen graphical interface, which allows you much more control over the furnace settings. It will actually allow you to control all three furnace zones completely independently, so you can set your target temperatures and your heating profiles independently for all three zones of the furnace. It allows you to store a lot more in the way of quality control information, so you can start entering information about sample IDs, sample serial numbers. It will automatically log the analyst who's logged in to use the HMI, so you have quality control information associated with the users of the system, and it keeps a much more detailed log of the runs that have been performed on the system. So by switching over to this controller, we've actually got a lot more capacity to control the system itself, but also to log usage on the system. So we're hoping that's going to make that a bit of a more user-friendly interface for furnace operations. It will still have the data logging function of the NanoDAC, so you'll still be able to log and download all the run information. Again, the Pyrolyser IV has the same layout on the electronics tray, so you can still remove the electronics tray, pulling it forwards for servicing. So those are the two sort of big changes on our sort of main Pyrolyser system. The next change is over onto the Pyrolyser Mini, and I think I've certainly presented to MPL's CARM meeting before, and I think I have to the Trischem user group meeting before. The use of the Pyrolyser Mini. The Mini was designed as a more compact furnace system. It's orientated vertically rather than horizontally, and it was designed to fit within fume cupboards or other sort of extraction enclosures. So the Mini doesn't have the capacity of the main standard pyrolyser. We can only process 2 samples at a time rather than the Pyrolyser's 6. But it is a more compact system, and it is easy to locate it within a fume covered environment. Now we've taken that design a stage further, and we've started to look at how the Mini can be modified to fit within a glove box or an active cell environment. And one of the challenges we have here is the ongoing maintenance, where there's a limitation on the size of components that can be transferred into the glove box or active cell, and there is a limit to what level of maintenance we can undertake within that environment. So we've designed this new version of the Mini. It's a modular construction which allows us to construct the furnace actually in situ, so that each component is suitably sized to go through the glove box apertures or the entrance chambers, and then to be readily installed to create the furnace itself. Likewise, the key components within that furnace system are now modular, which allows us to perform operations such as replacing heating elements much more straightforwardly, and that can be done using remote manipulators if needs be. So it's a much more easily maintainable system for these sorts of environments. And we're currently looking at how we can develop this system, both in terms of undertaking analyses of radionuclides such as tritium and carbon-14, but we're also extending it out to look at other volatile radionuclides such as iodine-129 and chlorine-36. And a lot of that will also transfer over onto the main pyrolyser systems. And I've definitely presented work we've done on chlorine and iodine analysis, and that's been ongoing and is progressing well. We're hoping to publish methods for iodine-129 analysis shortly, and chlorine-36 following on behind that. So quite a shift in design for us, but meeting certain requirements in terms of more high active applications. Linked to the Pyrolyser Mini program of development, we've also developed a new design of bubbler assembly. This allows you to actually trap your volatile radionuclide directly into a scintillation vial, so you don't have to trap into a bubbler solution contained within the glass bubbler and then dispense an aliquot of that out for liquid scintillation counting. The bubblers that you can see here, as I say, they are a 2-piece bubbler. The lower half contains the scintillation vial, and the upper half is in effect an anti-suck back chamber. So this ensures that the liquid can't suck back from the bubbler and up into the furnace. The ones that I'm showing here were designed for the Pyrolyser Mini, so they connect directly onto the work tube from below. We also have a modification which will connect to the standard pyrolyser, which uses a right angle connector. But again, we can connect those through ground glass joint connections to give us a good fit. Again, the design of these has the application of glove boxes or active cells in mind, so they are easily dismantleable and assemblable using remote manipulators if needs be. The next thing I want to bring to your attention, for those of you who use the furnace systems, is the platinum alumina catalyst. Now, traditionally, we have always used a 0.5% platinum alumina catalyst, which is supplied to us. The supply for that catalyst has dried up, basically due to overarching demand for it. It's not a particularly highly demanded material, and it's now been replaced with a slight variation, which is a 0.3% platinum alumina catalyst. So it's identical in terms of physical form. It's identical in terms of mode of operation. The only difference is that it has slightly less catalyst associated with it. The 0.3% platinum alumina catalyst is very much a standard catalyst in the precious metals catalyst industry. So we have a much more reliable supply of this material moving forwards. So you can see the photograph there, which shows the two catalysts side by side. You can see the 0.3% just looks slightly lighter because it has less platinum associated with it. We've undertaken quite a few tests associated with the use of the 0.3% platinum alumina catalyst, using a tritiated thymidine spike to try and challenge the catalyst a bit more. And we've operated the catalyst at 400 degrees centigrade, which is actually lower than we would normally operate the catalyst at, again, to try and challenge it a bit more. And what we've found is that under those conditions, we're still getting quantitative recovery of tritium. We're not getting any coloration in the bubblers at all. And the quench values that we see for the bubbler solutions are comparable to when using 0.5% platinum alumina. So we're confident that the 0.3% is functioning in the same way. So all new furnaces are now being supplied with 0.3% catalyst, and we are gradually transitioning over to 0.3% for our replacement supplies. There is a technical note which details a bit more of the testing program to hopefully provide confidence that the catalyst is performing in the same way. We're still maintaining our training programs, and we're still offering training across the range of products that we market, and that is normally done on a case bespoke basis. So we can offer training to individual organisations, or if it's been identified there's a particular training need, we can offer that across multiple organisations. And they at the moment can't be offered on site, but we can offer online training. So that's just something to flag, which is still progressing. And then finally, just to round up, just to flag the fact that the RADIC website has been modified slightly. We now have a number of technical videos which are actually hosted on YouTube, but which you can access via the RADIC website. So if you have a bored afternoon and you feel like watching some videos about the pyrolyzer systems, then you can now find a selection on YouTube. So that's a bit of a whistle-stop tour of some of the developments that we've been working on over the last 12 months. There's a lot of exciting new developments coming through, and I'll be happy to field any questions.
Oh, thank you very much. I'm certainly looking very much forward to the chlorine and iodine papers. That would be extremely helpful. So the first question was from Svetlana, who was wondering about the sample size range that you can use in the pyrolyzer.
In the pyrolyzer in general, it will depend on the sample type, the sample matrix that you're running. So, for example, we would normally, or we could run 20 grams of concrete quite comfortably in the pyrolyzer system, low organic content material. If you're looking at higher organic content materials, organic rich materials, it might be 0.5 to 1 gram. It also depends partly on the density, because it's really the amount of material you can fit into a sample boat. The only other proviso is if you are measuring carbon-14, there's obviously a limit to the amount of carbon you can trap in your carbon trap, and that actually becomes the limiting factor in terms of sample mass.
Okay, thank you. Next one is going to be a bit more wide. Any tips for chlorine 36 analysis?
Lots of tips for chlorine 36 analysis. So that we've actually been doing a lot of work on chlorine 36 and iodine 129. Iodine 129 is reasonably straightforward, and I think we've now got the technique working reliably for iodine 129 over quite a range of matrices. The chlorine 36 is more challenging, and there are a number of reasons. Partly it's to do with the efficiency of release of the chlorine from the matrix that you're trying to analyse from, and it's partly to do with the transfer of the chlorine once it has been liberated through the furnace. So we've been looking at various modifiers which encourage release of chlorine from the sample matrix to ensure that we've actually effectively liberated it, and we have slightly different configurations on the furnace itself to ensure that when the chlorine has been liberated, it's being transferred efficiently through to the bubblers. Once you've actually got it into the bubblers, we've then been using the Triscam CL resin for the chlorine iodine separation, which works very well. That side of it seems to be pretty robust. It's just getting it to that stage in the first place. But I think, as I say, we're hoping in the next few months we'll actually have the chlorine method in a robust form.
Okay, thank you very much.